Hello, students, and welcome to today's lecture where we are going to be talking about calorimetry, or basically how chemists can lazily find out how much enthalpy is changed in a system. This works for a whole bunch of reactions. In particular, calorimetry is a great way to calculate enthalpy when we have no change in work for a reaction. All right? So the basic idea is that if we don't end up evolving a gas or cause an expansion of volume, that we can go ahead and use calorimetry to go ahead and figure out some uh, basic functions of the energy that is being evolved or changed in that system. All right. But first, what we're going to need to do before we go much further in, we're going to have to go ahead and define a couple of things. Okay. And we're going to go ahead and show our manipulations here. Okay. So our basic formula for enthalpy, or a change in enthalpy, is that a change in enthalpy equals the change in internal energy plus any pressure volume work that it ends up being done. Okay. Internal energy, we can go ahead and state that as Q minus W. Okay. That would mean that essentially this unit here is W, and this unit here is W, which means that we would end up having Q minus W plus W, which means that if we have a case where we have internal energy and we have the work equaling 0, we're going to have delta H equals Q. And in this case, this Q is going to end up being like the change in heat of a system. All right. Now, there is a long derivation that we could theoretically do for this, but realistically, for any reaction where we do not have any pressure volume work occurring, we can just assume that delta H equals Q. And you'll know that there's pressure volume work occurring if you see like an evolution of a gas, or if a particular reaction makes a gas, you're going to think, okay, maybe this is something that I can't necessarily calculate using standard calorimetry, because it'll end up making pressure volume work. An example of that would be we would need to figure out pressure and volume for like a combustion engine. That since that's doing work, we need to go ahead and do more things for that. But for a lot of chemical processes, like when we're mixing chemicals together in class, you're not making a gas per se when that happens, therefore we can easily measure it. So that's the terms that we're going to use. The second amount of information that we're going to need is this one, and this is a heat change calculation. And it should be familiar to many of you, where we're going to have Q, and Q is essentially our heat, and we're going to use this Q here to help us with our delta H later, equals mc delta T. And m is going to be the mass of the substance that's absorbing or releasing heat. And more often than not, we're going to use water, because water is a great solvent. It ends up dissolving a lot of things, and we have really nailed down the specific energy of water. C is going to be the specific heat of a substance. That's how each substance responds to heat, whether it heats up quickly or if it heats up not so quickly. That's what's going on with that. If you've ever jumped into the pool on a hot day, you'll notice that the pool water feels cold, and that's because water heats up very slowly, whereas the metal that's around the pool will be warm. That's because the metal warms up quickly. Okay? So this is like the specific property of that compound that's absorbing or releasing that energy. And the last thing that we're looking for is a change in temperature, okay? And we're usually going to measure the temperature in Celsius. Since it's a change in temperature, you often do not need to convert it from Kelvin to Celsius, because Kelvin and Celsius measure in the exact same range. If you go up by 1 degree Celsius or up by 1 degree Kelvin, it ends up meaning that you went up by 1 degree. Okay. And we're going to go ahead and show a problem here. Now, most of the time, when you're doing what I like to call useful chemistry, if you're worried about figuring out the enthalpy of a reaction, you're going to be doing a reaction in water, and you're going to be finding out all of these things when you do the reaction. And later this next week, we're going to do this reaction where we're going to go ahead and calculate the heat change of it by doing the actual reaction itself. But for some processes, especially with testing, the other thing that you'll often find is that you might have to solve for C or delta T or M, but that in and of itself ends up just end up being like a plug and, do a little bit of algebra in order to solve it there. Okay, and then we're going to go ahead and, go into calorimetry a little bit more in depth here. Okay. Okay. So a reminder that heat is always going to flow from a warmer object to a colder object. Okay. And calorimetry is the way that we measure heat transfers. Okay. Any device can be used for it. There are fancy calorimeters. However, based off, if you are using a fancy calorimeter, all that's happening is that you have essentially made a very fine-tuned, like exacting looking device that holds all of the heat in. For our purposes, what we are going to do is we're going to use a coffee cup calorimeter. And a coffee cup calorimeter essentially just ends up being a styrofoam cup. And the reason that we use a styrofoam cup is that a styrofoam cup really retains heat well, which is why it's been used for coffee cups for so very long. Okay? And you just need to make sure that your cup has a thermometer in there. You need to have 2 cups, and then you need to make sure that it's stoppered up so that you don't lose any heat coming from the upside of the cup. Okay? And that's all that we're trying to do with a coffee cup calorimeter. We're just trying to keep all of the heat inside so that we don't lose any when we're making our measurement. Okay? All right. Usually what will happen here is that you'll go ahead and do your reaction mixture. Well, you'll measure the temperature of the initial state of the water. So your water normally will end up being at room temperature. And then you'll put your mixture or your stuff that you are mixing together in there, and you will get the heat flowing from the reaction. As the reaction's happening, it will evolve heat. And that heat that goes into the water is going to show us exactly how much energy was lost when that reaction happened. Okay. All right. The other thing that we could do is that we could also use this to go ahead and find an unknown metal. Okay. Because all different metals have different specific heats. If we're able to determine how much heat is evolved from a metal, we can use that to determine the specific heat of the metal and then the identity of the metal. Okay? And that's what I said right there. Okay. So first you'll have to put a known mass of water. Okay? And this goes with, the idea that what we're going to be using is this equation here, but what it's going to end up being is that we're going to have the metal, that we heat is going to equal Q equals MC delta T. But also the water that heats up is going to be Q equals MC delta T. Okay, and the main idea is that if we lose energy from the metal, okay, then it will go ahead and go into the water, and the energy that's lost in the metal will equal the energy that goes into the water. Okay, so we're essentially making these two equations, the Q in both of these equations ends up being the same. What's going to end up changing here in any type of find the specific heat of this metal question is going to be this C. Okay, the mass of both the metal and the water is going to be something that we're going to have measured, and the delta T is something else that we're going to have to measure. All right. So here we're going to go ahead and start with some water that's at 125 degree or 125 grams of water, and it's going to start at 25.6 degrees. Okay. We're then going to go ahead and heat to a known temperature. Okay, and I'm going to go ahead and this might be something that I want to go ahead and do. Heat up a metal and use like an infrared thermometer would be a good way to measure the temperature of that metal. Okay, so using an infrared thermometer, we heat 50 grams of a unknown metal. Okay, so that means that we don't know what it is, to 115 degrees Celsius. All right. The metal is then placed in the calorimeter. Okay. So we heat this lump of metal and then we put it into the calorimeter. Okay. Heat is going to flow from the metal into the calorimeter. Okay. And when that heat stops flowing, when your temperature stops moving up, that's going to be when you know that it's reached its equilibrium point. Okay. All right. And when it's reached the equilibrium point, or when the temperature has stopped leaching out of the metal, both the water and the metal will end up being at the same temperature. Okay. So in this example, the water went to 29.3 degrees Celsius. Okay. Which means that the temperature of the metal also went to 29.3 degrees Celsius. Okay, then we'll go ahead and use the specific heat formula to figure out the amount of heat that's transferred. Okay, and for here, Q equals MC delta T, we had M equals to 125 grams of water. The specific heat of water is 4.184 joules over grams degrees Celsius. And delta T is the final temperature minus the initial temperature. Okay. Plug it all in, and we find that we evolved or absorbed 1,940 joules or 1.94 kilojoules of energy. The heat gained by the water is also the heat lost by the metal. Okay. In this case, it's going to be negative 1,940 joules. Okay? So we can plug that back into the same equation where we have our Q, we have the grams, it's 50 grams, and we went, from, this is our initial 115 degrees Celsius to 29.3 degrees Celsius, okay, for a change of 85.7. Okay, which will go ahead and give us 0.453. Okay, notice that we're just solving for C. Our initial question has, we're just moving this C over here first. I find it easier to move it in when it's in its derpy mode and then just plug in our numbers. And that's how we solve it for C. A note on C, your heat capacity should always be positive. And if it's a metal, you should be expecting to have a low heat capacity. Okay. And here's an example of like different specific heats for different substances. And what you would normally do is you would go ahead and take your number that you have right here, which is 0.453, and you'd be like, oh, okay, so what was the metal that was involved? And you'd be like, oh, okay, it's 0.045. So it's likely that it is iron that we used in this experiment. Okay. One thing that I want you to note is that the specific heat of liquid water is important because it's 4.18. Okay. 4.18 is going to be one that you're going to want to memorize because we end up using it so often. I also want you to take a note that when we change states of water, that change in state also gives us a change in the heat capacity of that substance. Okay, so that absorbs heat differently because of that. At this point, that should be all that we need to go ahead and begin thinking about our specific heat of our calorimetry. And you should be able to use this information, especially in the lab that we have going on forward here. All right. And until next time, remember to stay lazy.